Okay. Good afternoon, everyone. Thank you very much for coming. Today I'm very happy to welcome Sam Livingstone from University College London. Thank you for delivering the seminar, and I'll let you continue with the talk.
Well, thanks very much. Thanks very much for the invite. It's really nice to be here. I've always wondered what it was like here, actually. But yeah, I'm gonna give the talk's going to be in two parts. The first half, I'm going to talk about some pretty established work now. It's been out for years, and we've been kind of extending it over the last few years, which is really on robust gradient-based Markov chain Monte Carlo methods. So we developed what I think is quite a simple algorithm that works quite well in a number of scenarios. It's not entirely clear exactly why in all scenarios yet, but that's kind of what we're working on. So that will be the first half of the talk. And then in the second half of the talk, I'm going to talk about more recent work, which is a little bit more biostatistical directly in flavor, and was kind of inspired by some work done here around about 2015, I think the paper was. So that's ongoing work together with a PhD student, Luke, and Gianluca Baio, who's at UCL with me. But I'll get onto that in the second half of the talk. So the first bit is about robust gradient-based Markov chain Monte Carlo, and the first paper connected with this was joint work with Giacomo Zanella, who's at Bocconi University, and then we did follow-on work with Jure Vogrinc, who was at Warwick for a long time, Max Hird, my PhD student, and Yorgos Vazdekis, who is my postdoc. But let's get into it. So this is kind of just setting the notation and the basics, really. Metropolis Hastings, pretty well-known algorithm. I imagine many of you in the room have used this quite regularly. It's the sort of workhorse of Bayesian computation. The idea is that you're going to simulate a Markov chain, which has a user-specified invariant distribution, and therefore you can kind of approximate averages with respect to that distribution by taking ergodic averages from the Markov chain. How does Metropolis Hastings algorithm work? Well, you're going to take the current state X, you're going to generate a possible next state to move in the chain. That's Y, according to this transition kernel Q, which I might call the proposal. And then you're going to choose whether or not you're going to go from X to Y according to this probability here, alpha. And if you decide that you don't want to go to Y, then you're going to stay put, and the next point is going to be X, right? And I think a lot of you will have encountered this kind of thing before. The big question in this algorithm is, how do you choose Q, right? How do you choose the proposal, right? What's an intelligent choice for this? And this is where a lot of the work has been done over the last more than 50 years, right? So one pretty simple choice, which actually is surprisingly effective, is the random walk metropolis, where you choose the next point based on sticking to where you are and doing some kind of random walk move, right? Very, very simple idea, but actually it's kind of, it's really stood the test of time. Slightly more sophisticated idea, the metropolis adjusted Langevin algorithm. There's various ways to motivate this, but you can really see it as taking a random walk metropolis and then taking some sort of move in the direction of the gradient of log pi, right? And intuitively, this does seem like a sensible thing to do. It's pushing me towards the mode. Okay, that's probably where a lot of the probability mass is going to be concentrated. So that's probably a reasonable thing to do. And then another one is Hamiltonian Monte Carlo. It looks a lot more fancy. Basically, you're kind of going to introduce some kind of momentum. Ooh. That's pretty good. I think I'm still screen sharing. Yeah. So you're going to introduce some momentum variable, which is going to be of the same size as your state variable. So you've doubled the dimension, and then on this kind of even dimensional space, you're going to run Hamiltonian dynamics. It sounds very fancy, but if you do a single step of Hamiltonian Monte Carlo, you're actually back to the metropolis adjusted Langevin algorithm. So you can kind of view it as a slight sort of generalization of this, where you're really moving further along the gradient path. And the main thing I want you to take from this slide, there's 2 points. One is that I've colored certain things in orange subliminally to make you guys notice them. And these are all the kind of free parameters that you get to choose as part of these algorithms. And the second thing is really the second two of these algorithms use gradients, right? They use the gradient of log of pi in order to help you design proposals that are going to be intelligent in some way. Right? So how do these methods work? What is known about what's good or bad about them? I mean, if you know anything about MCMC theory, you've probably come across these kind of scaling arguments, these kind of scaling limits, where you look at the algorithms in a high-dimensional setting, you try and relate them to some sort of limiting diffusion process, and then you look at the speed at which that diffusion travels. And it feels like a bit of a roundabout analysis, but you can connect this directly to mixing times of the Markov INF dimension. And if you look at that, it kind of tells you this thing, which basically, as the dimension grows, this is how the algorithm degrades, how algorithm performance degrades. The algorithms always get worse in higher dimensions, but the rate at which that happens is what we care about. And you can see that sort of MALA and HMC generally scale better to the high dimensional setting than the random walk metropolis. But there's a crucial subtext here, which is that this analysis looks at the algorithms at their best. If they're really well tuned, if these parameters that are highlighted on the previous slide are chosen intelligently. And if you're an applied practitioner trying to use these methods in practice, your natural question would be, okay, well, how do I choose these things? Is it easy enough to do? Are the algorithms like robust to if I make a slightly wrong choice? What happens in a practical setting? And that's really kind of where this kind of talk comes in. So I'll talk a little bit about sort of difficulties for gradient-based algorithms, and there's quite a few, but here's a couple of them that I'll mention. So one of them that's very classical is light tails, right? So this is when the gradient, the tails of your target distribution are extremely light, which means that the gradient of log pi tends to grow in absolute value extremely quickly. Right, the gradient's changing very quickly, which means that sort of simple ways of putting it into algorithms tend to cause problems. So we'll look at a simple example here. So this basically, if your gradient grows faster than linearly in X in some sort of sense here, then it's known that the algorithms don't perform very well in the sense that they don't produce fast mixing Markov chains. And there's a kind of simple intuition for this. I'm going to give an example that maybe the people on Zoom won't see very well, but I think it's not too bad if they don't see. You're not going to miss too much. But let's say the target distribution has a density that just looks like this. So it's quite light-tailed, right? It's a lot lighter than a Gaussian tail because you've got an x to the 4 here. So then that means that the gradient of log I is going to be minus x cubed. And so then if you think about what MALA does, your proposal is going to be the current point minus some step size times h cubed plus some sort of noise. And basically, you can see that whatever choice of step size you use here, if you imagine the current point x is 100, and x cubed here is going to be 100 cubed, right? So I have to choose an extremely small step size if I happen to be out in this tail of the distribution where I'm at 100 here to stop me from flying over here with my proposal, right? So this kind of very fast changing gradient is, if I use it in this kind of way, is causing this kind of serious instability in my algorithm. And in order to control for that, I have to choose a really small step size here and then just hope that I don't end up out really far in the tails. And this kind of instability is quite common in both MALA and HMC. That's good. Yeah, okay. So here's an example of where this feels like a toy model. Here's a pretty simple, real practical statistical model where you're going to see this kind of behavior, Poisson generalized linear model. If I just parameterize the mean function as the exponential of xi transpose beta, like pretty standard Poisson GLM, then that's what the gradient looks like. And this is actually going to be exponentially growing in beta, right? So this is worse than the example I just gave here, right? This is a pretty standard statistical model that you probably want to fit to data, right? But that's actually not all. There's more issues that you can encounter with gradient-based MCMC, and that's this tuning, this choice of these parameters that I touched on earlier. And I want to bring up a quote from Radford Neal, who's someone who is very much one of the most influential people in using gradient-based methods in Markov chain Monte Carlo. And he has this statement about Hamiltonian Monte Carlo, which is a method that he introduced into the statistics community. He said, look, it works really well, provided it's tuned properly. However, if you choose a step size that is too large, it's disastrous, right? And that's exactly this H that I've got here on the board, right? And this is the person that actually introduced it to the community as a really good method, was openly acknowledging that it has its problems. And you can see this really easily on an example. I haven't done Hamiltonian Monte Carlo here, but I've done MALA, and the pathologies are the same for the two algorithms. And basically what I've done is I've made the step size bigger on the x-axis, and then I've just measured expected squared jump distance, which is a fairly generic measure of how well the Markov chain explores the state space. So bigger is better, right, for this method. That's all you really need to think. And you can sort of see that if I make the step size bigger and bigger and bigger, at some point the performance of MALA starts to degrade very rapidly, right? Whereas for the random walk metropolis, which is a comparatively simpler method that's supposed to work worse in higher dimensions, actually, it's much more stable decline, right? So if you chose a step size which is a bit too large, it's not such a big deal. You probably get away with it. The blue line is the method that I'm going to introduce later, but I mean, now you can just sort of see how it works. Okay. So what are we concluding from this? Okay, so harder to tune, more unstable, with the different types of gradients you can encounter. Well, in practice, this kind of means it's harder to choose these parameters that are highlighted, which is crucial to the practical performance of the algorithm. And often in practice, the way we try and choose these these parameters is through some kind of adaptation, some kind of adaptive MCMC. And what we found with our experiments is that if you have an algorithm that is quite unstable like this, it can be that this adaptation goes really wrong, right? So if you have an algorithm that's a little bit more robust, it seems to have a real kind of blessing if you try to use it together with adaptive MCMC, right? So I'll show some experiments to kind of highlight that later, but I think I've got a little schematic here as well in the next slide. So just to sort of solidify what I'm talking about here, if you looked at the way I set up the algorithms here, I've kind of written basically the free parameter in the random walk metropolis is the covariance matrix of the proposal. And I've kind of written it, over-parameterized it deliberately as some sort of notion of global scale, and then some sort of matrix here, which is going to take into account the kind of shape of the distribution. And so you don't need to set it up like this, but I think it helps when you're thinking about adaptive MCMC, because you can think of sigma as this kind of global scale. How big do I want the overall jump to be? And then this kind of capital sigma to kind of decide on the shape of the jump, right? And typically then capital sigma is kind of chosen to be something like the covariance matrix of pi, which is something you'll try to learn from your samples. And then this is kind of chosen based on something that will achieve a desired acceptance rate. And that's the kind of idea. Okay, so yeah, my message is that this is much harder to do if the method is less robust. So here's a kind of simple example of why this can be hard. So if basically, this is just a random walk metropolis here, but the target distribution is kind of elliptical shaped things. And I've started a random walk metropolis with a spherical proposal, right? So just the identity matrix is my proposal covariance. And what you can see, what you're going to do is you're going to tune your global step size to match the smallest variance, right? So you're going to explore this kind of X component, component one quite quickly. But then because you've got quite a small step size to match that, it's going to take you a really long time to cover the much bigger direction here. And you kind of need to have explored the whole thing in order to get a good idea of the covariance structure to then precondition intelligently and choose these parameters. So it's a bit of a circular argument, right? And what you really want to do is be able to get away with a slightly bigger step size initially so that you can then make some jumps that are supposedly a bit too large, but actually you end up exploring the dimensions that you need bigger jumps for, right? This kind of connects with the previous graph I was showing, saying, look, if you've got a method where choosing a step size that's a bit too big is not a big disaster, you can make those kind of risky bigger jumps and end up exploring the state space much more quickly and then getting the kind of overall feel for the shape of the posterior. And that's kind of what we're seeing in the experiments. Okay, so we did kind of formalize this argument a little bit in terms of spectral gaps. So spectral gap is a generic measure of how fast a Markov chain mixes. Bigger spectral gap is better. And basically what we did is we made, we chose a fixed step size for our distribution, but we made the scale of the distribution, like the marginal variances, get really, really, really small, which means that the choice of step size you'll make is getting increasingly too large. And we looked at how fast the spectral gaps decayed to zero as a function of this like variance going to zero. So the idea is that if the spectral gap decays at a slower rate, then the algorithm is a bit more robust to choosing too big a step size. And yeah, we found that for the random walk metropolis, you know, the spectral gap decays to zero polynomially, but for MALA and HMC, it decays exponentially fast, so much quicker. And this kind of, to some extent, corroborates the empirical discussion we just had. Having explored the phenomenon a lot more, I think there's more going on than just the analysis we did here. There's some more mathematics to do, but that's certainly part of the story. So yeah, so that the message, the penalty for getting a step size too big is much worse for MALA and HMC than it is for the random walk metropolis, which means that it can be much harder to do adaptive MCMC with these algorithms. Okay, so yeah, so I don't know if it's worth going over this slide, but basically, if you're more interested in the mathematical side of things, this is how you would define a spectral gap. It's really just the current point in the Markov chain. If you imagine that you started the Markov chain at equilibrium and then you take one step and you're kind of looking at how far that one step takes you as defined by f of y minus f of x squared. And then you take the infimum over all f's. So it's kind of some generalization of what's called the expected squared jump distance. You're really looking at how far the Markov chain moves and how far it moves as defined by whatever this function f is. And then you choose the worst case. And so if you're more interested in the mathematics, this is the kind of where you start the analysis. But yeah, I'll skip over that. So yeah, so I've kind of led you now to the natural question of, okay, well, so the message we had so far was gradient methods are good because they scale really well to high dimensions, but gradient methods are bad because they're not very stable and they don't allow you to do adaptive MCMC very well in these kind of tricky scenarios, right? So we've got a bit of a problem, you know, can we fix this and find a gradient method that is still scales well to high dimensions, but doesn't have these issues of like lack of robustness? And of course, I wouldn't be standing here and setting it up this way if the answer wasn't yes. So here's a little bit more robust. We called it the Barker proposal. It's really hard to name things. I wish I hadn't called it this. I don't think it's a very good name. At the time, there was a method that just come out recently called the bouncy particle sampler, which goes to BPS. And I think we were trying to call this the Barker proposal scheme, which also abbreviated to BPS. And I thought it was quite funny to say a minute. Stupid idea. Anyway, there's some connection to Barker's acceptance rate for those of you that have some sort of familiarity with like old school MCMC ideas. but I don't think I'll touch on it too much in the talk unless people are interested. But it works in the following way. To generate the next state in my Markov chain, I'm going to draw some zero mean symmetric innovation, just like I would in the random walk metropolis. But then I'm also going to have this random variable b, which takes the values +1 and -1. And it takes the value +1 according to some probability. And then my proposal is going to be the current point plus b times xi. Right? So if we step back for a second, if I made this probability here a half, I would be doing random walk metropolis. Okay, so I sample some symmetric zero mean noise, and then I multiply it with something which can be +1 or -1, each with probability a half. Well, I'm not changing the distribution of that thing. It's still symmetric and zero mean with the same distribution. So that would be a sort of silly way of simulating a random walk metropolis proposal. What I'm doing is starting from that and saying, okay, well, instead of having b +1 or -1 with probability a half, I'm going to instead make the probability depend on the gradient, right? And this is a kind of generalization then where I'm bringing the gradient in. Yeah. And what's the message? Basically, so this variable b in one dimension, you can think of it as deciding whether or not to flip the sign of the initial proposal xi, right? What's it doing in a bit more detail? So if xi would take you in the direction of the gradient, then with probability more than a half, I will set b equal to 1, and I will go in that direction, right? Because it feels like, according to the gradient, that's a good idea, right? If they have opposite sign, however, then I'm more likely to flip it and still go in the direction of the gradient, right? So the proposal, it's not skew normal, that's a typo, but it's skew symmetric. So it's a skew symmetric proposal. I'm skewing in the direction of the gradient. That's the idea, right? So we can contrast that with MALA, where what you're doing is you're taking the same kind of additive noise xi, but then you're adding this kind of additive drift, right? Grad log pi. And the message is that this kind of skewing operation turns out to be a lot more robust if the gradient is a little bit unstable than just adding it like this. The reason for that is that the size of the proposal, y minus x here, is always going to be xi, right? It just determines, like, the direction is determined by the gradient. So you're not going to have this issue where you fly off into the tails of a distribution. If the gradient's extremely large, all that means is that with a strong amount of certainty, you're going to go in the direction of the gradient. But you've still got some control over the magnitude of your proposals. So a toy example, the current state x here, and let's say I'm just sampling from this one-dimensional target here. The gradient looks like this. I've generated my initial noise. It's in the same direction as the gradient. So with high probability, that's where I'm going to go, right? With probability 0.04, I would end up over here, right, with x minus 6. Pretty simple idea, right? Okay. In multiple dimensions, there's a few different ways you can think about implementing this, but in some sense, a simple one that we would class as like the canonical way that works very well is to just do this kind of component-wise. So you have your B now becomes a vector of the same size as your state space, and you sort of element-wise multiply that by xi, and each B is probability +1 or -1 based on the partial derivative of log pi in that direction. And this is kind of what the proposals might look like. So this picture on the left is quite informative as to what's happening as the gradient gets larger. You're leaning towards a kind of truncated normal proposal in the direction of your gradient. Right? So this thickest red line here is a situation where the gradient is very large. Right? Good. Okay. Cool. So where did we come up with this? How
The gradient is very large in that situation because the tails are very thin. Is that?
Yeah, I mean, we were just, so you certainly could have a large gradient in the case when the tails are very thin, yeah. I mean, but even I mean, any situation where the gradient would be growing, for example, the further you go out into the tails, the more your proposal is going to look like this kind of truncated thing. Yeah. Okay. So how do we motivate this thing? There's a couple of ways you can do it. One is to think about a class of Markov jump processes, which is pi invariant, and say that, okay, the proposal is kind of based on this. And this is a new class of processes. I mean, I'm sure people have thought about it before in some area of mathematics, but we've been studying them for the last few years, and we call them locally balanced jump processes. There was a paper written a couple of years ago on discrete spaces where they called it the Zanella process after Giacomo Zanella, who's my collaborator, but hasn't really caught on yet. But maybe maybe it will. But yeah, we've been studying these for a while. There's actually another way to motivate it based on more recent work, which perhaps I kind of like. You can think of, just like MALA is usually motivated as a way of discretizing this Langevin diffusion, the overdamped Langevin diffusion, using the kind of vanilla Euler-Maruyama discretization scheme. That's the typical way of thinking about MALA, because this is a pi invariant diffusion process, but you can't simulate it exactly. So you do some kind of numerical scheme, and then you use it within Metropolis-Hastings. You can instead think about using a different numerical scheme, and it turns out that if you can think of the method that I introduced as a kind of skew symmetric numerical scheme for simulating the Langevin diffusion. And it's weak order 1, the same way that Euler-Maruyama is, but under much more stable conditions on the gradient. So this is work that I've been doing with my postdoc Yorgos Vazdeikos and Nuskin at King's. So that's another way, if you're more familiar with kind of the Langevin diffusion, if you've worked with MALA in the past, that's another way you can think of this algorithm, just a more robust discretization of this diffusion. Okay, so some numerical experiments, right? So this is a Poisson random effects model, and there's a few graphs here. So we're running MALA, random walk metropolis, and this Barker algorithm. And the top 2 rows are the adaptive MCMC parameters, right? I've got this global scale on the top row, and then I've got the diagonals of my kind of preconditioning matrix that's determining the shape, the relative scale of each component on the second row. And then the bottom 2 rows are trace plots. And so if you first look at the global scale and the preconditioning matrix, you can see that basically MALA is really struggling to find intelligent adaptive tuning parameters in order to run the algorithm well. Right? And the reason for this is, for this particular model, it's an extension of the Poisson model I showed earlier, with just more mess in it, more random effects, more crazy stuff going on. So the gradients are extremely unwieldy. And it's also something quite difficult to just reparameterize your way out of. If you do a sort of typical reparameterization, you get a big spike at 0, otherwise you get something growing very fast in the tails. And it's really struggling to sort of find the right choices of parameters. And so as a result, the sampling isn't very good. Random walk is a lot more stable because it's a lot more stable algorithm, but because I think this is a 100-dimensional problem, so it's not really aggressive, but it's a little bit more than toy, and you can see that dimensionality kicking in with the random walk metropolis. It's struggling a little bit to find the right kind of parameters, but once it gets there, it does okay. And Barker does a lot better. So in this particular example, it does feel like it's getting the best of both worlds. It's not always going to be that way. We've tried other models where MALA does better, but our argument is that Barker never does too badly. Here's the same model, and we also tested it out with kind of HMC and NUTS. So NUTS as inputted into the STAN package, which is an excellent package and a very much a kind of gold standard for gradient-based MCMC if you really want to test out a method. And we basically tried 3 different sets of kind of hyperprior choices for the model, and if you kind of had sort of easier hyperprior choices, then NUTS was doing about 2 and a bit times as well as Barker in terms of effective sample size per gradient evaluation. But when you got into the sort of more difficult choices of hyperpriors in terms of how unwieldy the gradients become, then Barker starts to do quite a lot better than NUTS here. A couple of orders of magnitude here. So yeah, so it's difficult to compare these algorithms in a fair way because they're being implemented on different software and things like that. So we went with ESS per gradient evaluation, but yeah, we did sort of find these results quite interesting. Okay, right, good. Right, so yeah, just to wrap up the first bit of the talk. So I'm certainly not saying everyone should stop using things like HMC. It's a very powerful algorithm, and I could have shown you lots of examples where it outperforms Barker. But what we like about this is a very simple, robust, and efficient method. It's really simple to explain. I could teach this quite easily in an undergraduate module. You know, I think there's a place for it. So we've done some more recent work thinking about optimal acceptance rates, just like in MALA and HMC, and we found it's the 57% magic number that's exactly the same as MALA is also appropriate for this. That was together with Jure Vogrinc and Giacomo Zanella. We also wrote a kind of tutorial paper, I think it's called A Fresh Take on Barker Dynamics for MCMC, and that's where we really kind of lay out the method in some kind of in a kind of fairly didactic way. So if you're kind of interested in getting to grips with the algorithm a little bit more, that's probably the first place to look at. So that's together with my PhD student Max Hird and Giacomo Zanella. Yeah, and now with my postdoc Yorgos, we've been looking at the foundations of these processes that I introduced, and also things like if you run Barker in an unadjusted way as this kind of alternative numerical scheme for a diffusion, what kind of error are you introducing if you don't do Metropolis Hastings, and various other extensions like that. So yeah, but yeah, and that's the original paper. But like I said, there's a couple of others around now. Cool. So that's the first part of the talk. Probably makes sense to pause if there's any questions about this now before I move on to the second bit. Yeah.
I was just curious, in your 100-dimensional puzzle example, you say you're doing this component, so making up 100 groups. You're using the gradient evaluation.
Yeah, so it's like a global MCMC move, in the sense there's one move in all 100 dimensions with one acceptance rate. Just in order to construct the proposal, you generate 100-dimensional Gaussian, but then each of the coordinates, for each of the 100 coordinates, you generate a B to decide whether it's a flip. So it's not like we're not doing something crazily expensive. You need to evaluate the same number of partial derivatives as with MALA and HMC.
But is there no, conceptually, would there be any advantage in being more clever about that?
Yeah, we've thought about this for a long time. I mean, the one thing that's annoying about that is it is kind of coordinate based. You know, whatever your coordinate system is, that's how you're implementing the algorithm. So if you reparameterize slightly, you're doing things in a different way. We basically explored another way of doing it that was a bit more geometric in this paper, but it didn't work very well. And we've since thought quite a lot about whether thinking about, you know, maybe thinking about sampling on hyperspheres and doing things that way. But we haven't fallen onto something that works better yet. It's a good question. Yeah, we're still thinking about it because that is an annoying bit. But
Thank you very much. Going back to that table where you compare the models. Yeah, this one. You said it's difficult to actually compare them, but if I may ask, how do you not compare the best one compared to the backup?
compared to
How do you compare your model compared to others? Do you have a standard model?
standard mode of comparison, you mean?
Yeah.
So I'd say empirically speaking, this kind of effective, usually some sort of summary of effective sample size, normalized in some appropriate way to take into account different computational costs, is what most like empirical comparisons of MCMC algorithms would do. And so that's kind of what we tried to do here. I think that we've basically, the way we've normalized for computational cost is by counting the number of gradient evaluations needed for a single iteration of the algorithm. And in many scenarios, that is going to be the dominant cost, but in some other scenarios, it's not. So that, I guess that's why I was putting a slight caveat. But
That's in terms of costs, right?
yeah, exactly. So you could probably engineer scenarios where that's not the dominant.
About this time.
Yeah, so you could also, the issue, if you're running everything with the same software, you've coded all the algorithms with the same software and running it on the same computer, then I think wall clock time is a very fair way of doing it. But in this case, we're just using Stan vanilla software. So that's got C++ running under the hood. Whereas the other algorithms we were just running in like R, or so it's not really, it wouldn't really be fair to compare them on that way. Yeah. Yep.
Because you mentioned MALA is not geometric ergodic, is the Barker proposal ergodic?
Yeah, that's a good question. Yeah, so in this light-tailed setting, yes, it is. So yeah, exactly this kind of setting here, where you've got this kind of gradient that's growing faster than linearly. That's when MALA and HMC are both not geometrically ergodic. It's not the only setting in which they're both not geometrically ergodic. Heavy tails are also a problem. Barker solves the light-tailed problem. It doesn't solve the heavy tail problem. So if you've got heavy tails, gradients on their own aren't going to do anything for you, because when you go out into the tails, the gradient just becomes nothing, just becomes zero. So it just doesn't help you move across the space more efficiently. If you've got light tails, the gradient's giving you great information, but you've got to use it intelligently, basically.
Could you quickly go back to the slide where you were comparing the algorithms when you increase the step size and
Yeah.
because I wanted to see what's on the y-axis.
This one?
Yeah.
It's just expected square jump distance. Yeah.
Your sort of methods comparison. Do you have sort of an intuition why nuts is performing so well?
Yeah, it's a good question. So they do a lot of work in the early stages of the algorithm to try to adapt the step sizes and all the different parameters in as intelligent way they can. They have this kind of heuristic right away, which tries to get them in a good ballpark. And then they have several different kind of epochs of like adapting and then readjusting and adapting and readjusting.
So it's really sort of fine-tuned.
Yeah, so I think it's been very well engineered, basically, the software. And I think one message of the when I visited the nuts developers, that was the way I pitched it to them, was that the message is that if you're going to use HMC, you have to have some really intelligent computer programmers designing really intelligent adaptation, just like you guys. But which I think is actually true to some extent. You know, that kind of explains HMC was around for a long time, but it wasn't really until Stan came along that people started using it a lot. And I think that kind of explains to some extent why that was. You know, that it's actually quite difficult to use in practice unless you've really worked quite hard on how to choose these things. Yeah.
Motivated the Barker method as an alternative numerical scheme for the diffusion solution, right?
Yeah, so that's more recent stuff. Yeah.
Is it like, can you make an analogy for the leapfrog integrator? Like, could you make a similar analogy to?
Yeah, I see. We've been thinking slightly differently in that case. We've been trying more recently to design versions of HMC that look a bit more like Barker, but that you can run multiple steps. And we're getting somewhere actually, but it's more about changing the kinetic energy in the HMC algorithm so that the overall move, you have a combination of changing the kinetic energy and kind of doing some other tricks, which then suddenly make a single step look a lot like Barker, in the same way that a single step of vanilla HMC is MALA. You know, not exactly Barker, but looking similar. So we've been playing around with those ideas for a few months now, but it's pretty early stages. I think we've been thinking about slightly differently to just an alternative symplectic integrator, which is a little bit more involved. I'll just move on to the second bit because it is shorter, so that should be okay. I'm conscious of time. So let me just check that I'm showing the right thing. Cool. Okay, so this second part of the talk is joint with my PhD student Luke Hardcastle at UCL, and also the co-supervisor is Gianluca Baio. And yeah, I don't know if my hair was better then, but it was. So, that's a couple of years ago. Okay, so this is more ongoing work, but I wanted to introduce it because it's really based on stuff done here, and it's quite a biostats thing. But I'll just spend about 10 minutes because of the time, which is okay because several of these slides I think I can skip. So one of it, which is these, right? I'm imagining you guys are quite familiar with survival analysis 101, and this slide is more for myself because I'm very much a non-specialist. But so we've got some kind of censored data here, got some kind of times, some sort of censoring indicator, and then some other covariates that we might be interested in associated with some individuals. Yeah, that's what I just said. And then we're going to form some kind of parametric likelihood function from that based on the data that we've got. So if the data is censored, you know, we only know that the event happened after what was recorded, right? Okay, so the classical notation, we've got the survivor function, and we've got a hazard function. And yeah, I'm hoping that it's reasonable to just go through this pretty quickly with you guys, because my feeling is that this is the stuff that you'll be very familiar with. So you can write this likelihood purely in terms of the hazard and survivor function. And you can also kind of relate the survivor function to the hazard function like that. So, you know, because you can express everything in terms of these quantities, it's kind of evolved as a reasonable way to work in this field, to think primarily in terms of the hazard function. So everything can be expressed in terms of this hazard function. So when you're modeling survival data, we often just focus on this. So what is a polyhazard model? Again, many of you may be very familiar with this more so than me, but so if you imagine the event time being the minimum of several different possible events associated with different risks, then you will induce a kind of additive hazard function, right? So the hazard function can be written as a sum of lots of individual hazards associated with each of the possible risks. Right? So one of the things could be, if you're talking about mortality, one of the risks could be just generic all-cause old age mortality, and another risk could be, you know, a car accident or something. So there's different risks, and you can set up your modeling this way. Right? And this is what you would think of as a polyhazard model. Okay. And one example of that would be the polyweibel, where each individual hazard is chosen to have the following form here. Right. That's a pretty typical choice of form of the hazard. So in the polyweibel model, you could also say, okay, well, I'm going to let this shape nu, the rate lambda, also be functions of covariates, right? So I can bring my x's back into the model and model the hazard for each individual patient based on the characteristics of that patient. Why would I want to do this? Well, so an individual Weibel model, you can generate the following kind of hazard shapes. You can have an increasing hazard, or you can have a kind of just a stable hazard, like exactly like the exponential model. Or you can have a decreasing hazard, right? So the Weibel gives you a certain amount of flexibility, but it doesn't allow you to have more elaborate shapes than this. If, however, I have a poly-Weibel model, I can get away with different type. I can have different types of shapes, and one particularly appealing shape for certain types of applications is this bathtub, right? So the idea is that, for example, I mean, the most common application we've looked at is a transplant surgery. Immediately after the event, there's quite a high risk of something going wrong, but as long as that sort of immediate period is kind of got through okay, then the risk goes down quite considerably before finally kind of other risks come and kick in as time goes past. And so you end up with this kind of bathtub shape. This is not the greatest bathtub in the world, but I think you get the drift. So the point is that this is constructed, this bathtub, of two different risks being added together, one of which is decreasing and one of which is increasing. And so you can kind of separate out the individual risks, individual hazards associated with each risk through the modeling. And the idea is that this is quite an appealing way of, you know, modeling this data, which kind of gives you some flavor of the kind of flexibility of a non-parametric model, but it's not fully non-parametric, and it's still got some kind of control over interpretability and Particularly in health economic contexts, what they're usually interested in is extrapolation. And I think if you're using a purely non-parametric model, the extrapolation is quite difficult. You need a lot of data in order to understand what's going on there. So sticking to a kind of flexible parametric form is quite important for them. So if you move beyond the polywiable and you have something like log logistic hazards in there as well, then you can get more interesting shapes, right, where you have a kind of slight delay before a big risk. And then this perhaps relaxes slightly into different kind of risks going forward. So you can move beyond polywiable to more kind of polyhazards and get more flexible, but still parametric models that way. Right. So what we were primarily interested in this project is Bayesian computation for polyhazard models. The story of the project really starts with this paper written by people who I think were all at the BSU at the time. I'm not entirely sure, but I think that's the story. And we started co-supervising Gianluca and I think 2.5 years ago now, maybe 1.5. No, 2.5. And he basically brought this paper and said, look, I think this stuff is interesting. Maybe we should have a read and see if we can develop it. So I had a read of this paper, and there were a couple of things that jumped out at me. One was that the idea in the paper is to fit these kind of polywiable models to data, but it's very difficult to know how many components should be in the polywiable model, right? Should it just be a single wiable model? Should it be a biwiable model? Should it be a triwiable model? And should you have covariates on the rate and the shape parameter, and how many covariates in each case? And the way they assessed this was with fitting individual models and then comparing them according to some reasonable criteria, which is perfectly sensible, pragmatic thing to do. The second thing was that there's some serious computational challenge in fitting these models. This is kind of mentioning that this took around 22 hours to fit the MCMC, and there's various reasons for that. But yeah, so both of these things, I thought, okay, maybe we can do something about this. And so the idea we came up with is building into the computation kind of automatic model and variable selection. Right. So rather than fitting several different models with and without covariates individually and then comparing them according to some kind of deviance criterion, we perhaps can put a prior on each of these kind of models and set up the MCMC so that it automatically samples from this kind of larger model space and gives you posterior model probabilities for each of these models. And that way you just need to run the computation in one go. And it does all this choosing for you. And so we thought that if we could get that running, it might be a slightly more elegant solution. So how are we going to set that up? Well, obviously, if you're going to do that, you need to put a prior on the kind of models that you're thinking of. So for the number of hazard components, we thought of various different priors. Initially, just a straight uniform prior, but then as we got a bit further into the modeling, we realized that it's kind of more beneficial to have some sort of parsimony. Otherwise, in the MCMC, you get kind of new components being sprouted and then dying all the time. And perhaps that wasn't something that we wanted. So we've played around with different choices of prior like that, fairly simple. And then you want these kind of what's called a spike and slab prior for the coefficients. So you want some mass at each individual coefficient of your covariate being 0. And then you want some mass at it not being 0. So this is the slab and this is the spike. And we just had Gaussian slabs, right? This is a fairly standard way to set up a pure variable selection problem, usually in a linear regression context. And I've worked with a different PhD student and my co-supervisor, Jim Griffin, on MCMC for this kind of variable selection in linear models. Doing it in this kind of setting where the likelihood is not, as amenable, and you're also trying to sample between different model spaces, in addition to this, is a lot more challenging.
So I'm sorry, in the first case, did you use reversible jumps? Or...
Yeah. So I'll get onto it if I can very quickly. Yeah. but yes and no is the answer to that.
Okay.
Right. So what's the computational challenges? Sampling from spike and slab distributions is pretty challenging. You can't just do like a random walk metropolis move because you'll never hit this spike at 0. Right? It's a continuous move. You'll never land exactly at 0. You need to do something better. So the variable selection solution, which is what's done in kind of traditional variable selection samplers, is to introduce an auxiliary variable, 0, 1 space. And if you're in a 1, you're on the slab. And if you're on a 0, you're on the spike. So that works pretty well if you can marginalize out beta and work purely on this 0, 1 space. And that's what's done in the kind of variable selection sampling community. You can do that basically if you've got a Gaussian likelihood. Outside of that, it becomes much more difficult. You can still do it, but you're doing a lot of work. There's a different solution which is very popular, very new, which is to use these kind of piecewise deterministic Markov processes. These are continuous time, non-reversible Markov processes that can be designed to be pi invariant. It combines deterministic dynamics from ODEs with Poisson process jumps. There's no diffusive behavior, which kind of crucially means that often you can simulate these things exactly in continuous time. The diffusive behavior is what makes it quite hard to do this usually. And you have this kind of almost surely piecewise continuous sample pattern. This is really important, actually. It's a really important part, and I'll show the picture of why this is. Basically, because of this, you can sample directly from spike and slab distributions. You're moving in a continuous path. And so if you want to travel from the negative to the positive side of your parameter space, you're going to have to cross 0 exactly. So then when you hit 0, you can choose to stay there for a bit, right? And that means you can sample from these distributions much more easily. I'm going to skip this slide on how the PDMPs work and just get to the picture. And this on the right-hand side is really showing you what I just described. You're sampling a one-dimensional parameter here, beta, which has a spike and slab distribution. And what's happening is you're hitting the spike at 0 for a bit, you're sticking there for a while, and then you're moving on. And you know, the amount of time you spend at 0 is kind of determining the weight associated with the spike. Right? So these are what these kind of PDMPs look like, and a particular type of PDMP that allows you to do this. There's two different versions. They're either called sticky or reversible jump PDMPs. So basically, we're using these ideas in 2 different ways. The first one was reversible jump Metropolis Hastings for the number of components, combined with the sticky PDMPs within each number of components to do variable selection. And it worked quite well. Yeah, there's some details that I think it's not worth going into here. But then we wanted to do something perhaps a little bit more elegant and say, well, can we also explore the number of mixture component, the number of hazard components within the PDMP, and just have a single PDMP which is doing all the kind of component and variable selection in one go? Feels quite satisfying if we could get that to work. And actually we can. So particularly for the poly-Weibel model, there's these kind of known non-identifiability issues that if you have 2 different hazards in your model that have the same shape, then actually they relax to being a single hazard, right? Where the rates are added together and you've got that shape. And actually, so yeah, you collapse to a single Weibel. And Luke noticed that actually this perceived, difficulty can be turned to our advantage here, right? So we can actually exploit this to design a kind of split and merge PDMP, which allows you to reduce or extend the number of components in your model. So you kind of, basically you have this kind of PDMP running, 2 different PDMPs running on each component. And if the PDMPs join together, they'll stick together for a period of time. And that effectively means you've reduced the number of hazards by 1 because of this non-identifiability thing. Your 2 hazards just become a single one with the rates added together. And so and then after a period of time, you can break them away. So there's a kind of split and then there's a merge move. We can also design continuous time birth and death moves, just like in discrete time reversible jump MCMC. And I'll just show you a picture so you can see the gist of what's happening. So at the bottom here is telling you the kind of number of hazards in the model at that particular time. So the orange here, you've got 3 hazards, because you can see that here 1 hazard is split off into 2. But then at some point, the kind of shape parameters become equal again. So you relax down into 2 hazards and then 3 and 2 and 1. And here, this was with the uniform prior. So you can see here, you have these kind of instances where a hazard is kind of born, is split off and then very quickly merges again. So that's how we found that having this kind of penalizing prior kind of reduces that kind of behavior a little bit. You can also do these kind of birth-death moves, just like discrete time reversible jumps, and they're a little bit more intuitive, perhaps in a way to understand. But yeah, the main message of this bit of the talk is that we did sort of manage to design schemes which everything can be done in this continuous time PDMP. So in terms of elegance, that feels nice. There's also a question of, you know, does it actually perform better than just doing the reversible jump? But it does appear that it does. So we have kind of split and merge type PDMP moves here. And this is the run time in order to get a single effective sample size, or probably more than one, I think. But and then we have the reversible jump here. So the smaller numbers are better here, and we were sort of doing better here. So at the time I made this graph, we were struggling to put these two things together in a single sampler, but now we've managed to do that. And actually they're kind of complementary to each other. So things actually work a little bit better when you have split, merge and death moves. But the message of this slide is that, yeah, it does seem to do better to have everything running in continuous time through the PDMP than to have the reversible jump moves in discrete time. Yeah. So this is very much ongoing work. But we're interested in polyhazard models because they fit it very nicely within the kind of nice guidelines, and you know there is an interest in facilitating use. So we're sort of currently defining, you know, refining the kind of inference, and we're mostly there actually with that part now. And so then, you know, the next steps are to sort of think about, you know, refining the prior choices and making sure the predictions are sensible, and then trying to eventually design this all within a kind of a function within one of Gianluca's R packages, you know, where someone can just press go and this is all going on under the hood. But yeah, okay. So I think I'll stop there. So thanks for listening to all of it, and questions.
So with your competing, so is that a competing risk you're having? Sorry, doing it.
Ask me a hard question on. But I don't think it's quite the same. It is a response I've overheard someone else say before.
You don't have two distinct outcomes. You're taking the minimum.
Yeah, I think it's
complicated single hazard.
Yeah, exactly. Yeah, I think it's slightly different. Yes.
The number hazard model, or this number of events that then make up the one event you're looking at.
Yeah.
That you know of.
No, so that's one of the things we're trying to learn. Exactly. Yeah. So of course, what you're probably trying to learn in practice is, you know, not every single one, but every one that can be distinctly recognized from the data, right? So you might have a composite hazard, which is like kind of all cause mortality, apart from the couple of things that you're particularly interested in. And it depends on the choices of hazards that you've made, how flexible you would want to go. I think with a polywiable model, you know, there's some difference between 2 and 3 hazards. Beyond 3, there's not that much flexibility you can actually get in the shape of the hazard beyond having 3, because you've already got some going down and some going up, maybe one just straight. If you're choosing, but if you're thinking about having possibly different hazards as well, then you might, you know, the log logistic throwing in as well, you can quickly sort of be thinking about potentially a lot more different components that you're considering putting in your model. And when you throw the covariates in as well, then you might only be interested in a bi or a tri-wiable, but whether or not each component has 2 or 3 covariates on it, suddenly you're in quite a big model space already. But yeah, so yep.
Okay, sorry. Looking at that polywiable hazard, is it the same thing as when we're looking at time varying covariates? Varying covariates, where covariate varies with time.
Yeah.
No, and in sometimes where maybe might take the form of kind of functions, you know, where the covariate varies according to the particular functions. You understand, function of time. So, and when you look at the hazard for that as well, it gives you different hazard at different time.
Different times too.
Is it the same way, or the same thing?
Well, I guess, so if you've got covariates in your hazard, right, then those covariates depend on time, then, you know, the hazard is then going to depend on time, right, in whatever way the covariates are dictating the functional form you've chosen in your hazard. So you can certainly get these kind of effects, you know, where like the hazard is changing over time if your covariates are playing that role for it, right, I guess. Does that make sense?
Right.
Does that answer the question?
Yeah, but can we use this polywebber as that when we have such
You have that kind of,
covariate?
basically you're mainly interested in how the hazard changes over time.
Yes.
Well, yeah, you could. I mean, the obvious thing to do would be to put time in as a covariate, but I think if you're interested specifically in how it changes over time, maybe a non-parametric component of the hazard, which is based on time, is probably might be a better way to do it, unless you have quite a specific idea of the functional form of how it depends on time. So you can get certain, basically the nice thing about the polyhazard is it gets some kind of interpolation between the parametric and the non-parametric. You're not getting to the fully non-parametric regime where you can have very, very flexible forms, but you're having enough flexibility that you can capture kind of lots of typical forms that are seen in applications. So if you really don't have any clue of what the form should be, it's probably better to go non-parametric. But if you have some inclination, oh, it might be a bathtub shape, it might be this kind of up and then down and up again shape, which seems to be quite common in these kind of health economic applications, like after transplant surgery, for example. That's when this kind of is useful because you're staying kind of parametric to some extent. The long-term predictions are a bit more stable. Yeah.
A really stupid question. On the slide immediately before this one, there is a bullet point which says preconditioning under lane switching.
Yeah.
What does that mean?
It's not really something that I touched on in the talk, but yeah. So there's samplers. You can have this kind of, I don't think I've got any examples on the slide, but basically each hazard that's active, you know, kind of, you can have a phenomenon where one particular like PDMP here jump to be sampling from like a different active component of the hazard, and it's kind of like the label switching problem in mixture models, and so this it's a bit of you can try and control for this by using an ordering constraint, but it doesn't completely control for it. If you have one distribution that's very peaked and another one that's much more vague, you can have them switch roles without actually one crossing, you know. And so we did encounter this issue, and the real issue is that the shapes of the different parts of the distribution that you're exploring here are very different, and so you'd want to use a different set of tuning parameters to explore this shape than this shape. So then if the samplers are switching roles, suddenly the set of tuning parameters you're using is the wrong one. So to the first part of the talk where I was talking about choosing tuning parameters intelligently, that's quite hard here, basically. So at the moment, we were just using kind of vanilla just not really using any preconditioning matrix, because when we tried to do that, we had this kind of problem of things switching around and it being very difficult to choose something sensible. But we have some ideas that maybe we could, you know, have something semi-intelligent in the sampler figuring out when you've jumped. Maybe. Yeah.
So in this kind of parameter space, what was the effective sample size? For which parameter was the effective sample size? Is it?
Yeah, okay, that's a good. In this graph here, honestly, I don't really remember. But, the main thing I would say is that when I made this graph, it was a few months ago, and I think the numbers are all off now. You know, we did, Luke refined the code quite a lot, and he did manage to get these numbers down quite considerably. It does take, you know, we are talking hours to run these things. You know, it's not something that's going to run in minutes, but it's definitely is sort of for the models that we've tried. We're talking a few hours. We're not talking like hundreds of hours. So on a just on a laptop computer, you can run it, but it sort of depends on the application. But you can have these things running for the order of kind of hours. Yeah, sometimes it's minutes, but you know.
Well, a question was like, is the effective sample size for the number of components or for the number of?
Yeah, okay, yeah. I can't remember what this graph was showing, but it says on the bottom actually. It says for the number of components. Yeah.
Like the other thing I was wondering is that, so the spike and slab prior, like the one you have, does it promote the same number of covariates regardless of the number of components? I mean, does it make sense to say that if I have more components, I would probably need less covariates to have some parsimony or
within each component? Yeah, that's a good question. We didn't build it into the priors for the number for the spike and slab priors, how many covariates, how many active component hazards are in the model, but you could, right? You could put more weight on the spike depending on what K was. We haven't thought about that, but it's a good suggestion. It could be something you could try to make things a little bit more parsimonious. Yeah, I don't know. It doesn't sound stupid to me. So yeah, it is something we could think about. Yeah.
So if the rates depend on regressors, we could also do variable selection on the variables that you would put in the as regressors when you pick the rates. Does it make any sense?
That's what we're doing, right?
Yeah.
Is this what you mean? Where is it? Yeah, this bit.
Oh, there you go.
Yeah. So that's what we're doing. Yeah, so we've got a number of components being chosen, but then also within each component, do you want covariates on the parameters or not? Yeah. So that's the kind of variable selection bit. Yeah.
I don't see any other hands, and I don't see any hands in the Zoom. So in that case, let's thank Sam again. Very much. You can stop the